So what we're looking at here is, again, some examples of solving trigonometric equations, but this time we're starting to play around with our curve. We're starting to think about, well, we know our normal sine curve, cosine, tan curve, they exist quite nicely in the number plane, but what happens if that curve shifts sideways, shifts up and down? What happens if we compress it in or stretch it out? These kind of questions start to get at the heart of all, how would we solve those type of situations. So here we're going to look at this question here, and this question says solve sine of 2x equals negative half. I think the first thing that I would want to drag out of this question here is that I see this idea of sine of 2x. And what does sine of 2x give me when I think back to my period with my curve, and what does that result happen in my curve? Well, we know that the period of a curve was 1 on a. 1 on whatever number is multiplying that degree. So here we have half. So because I have a period of a half, what I end up here is, instead of my normal sine curve going between 0 and 2 pi or 0 and 360 degrees, what's actually happening now is that that's reduced by half. It now goes between 0 and 180 degrees, or 0 and pi, if I'm talking in radians. So that has an impact on my curve. It has an impact on what happens with the result of my answers. That whole curve is now squished in. So just scrolling over here to the right and seeing this is what the solution would look like graphically. So you can see the red curve is y equals sine of 2x. And you can see it's happening twice in that 2 pi, that 360 degrees, because of that 2 in front of the x, that change of my period. Because that's changed, all my solutions have moved as well, where they normally would have been compressed, dilated towards the y-axis because of that change in period. So how would we go about and solve for this? And quite simply to put it, let's pretend the shift doesn't happen. Let's use what we know, and use what we know really well, which is just the normal sine curve. And how can I use the normal sine curve to get the result that I want? Well, if we look at this one here, I can see with this curve, this compression of my period by half, so it's squished in, that over the 360 degrees, or the 2 pi that this domain has asked for, my curve happened twice, two full cycles because of that period. So I'm going to take that, I'm going to use that to my advantage. Instead of solving it all squished up over 2 cycles, let's do sine normally. So what would 2 cycles be normally? 2 cycles would normally be 720 degrees, or 4 pi. Everything has stayed in its normal location. I have one set of answers in between 0 and 2 pi, and then I have the exact same set of answers, but just shifted it, repeated it again in the next 360, or the next 2 pi. So I'm going to take that idea that I know how to find all my solutions between 0 and 2 pi. Those same solutions are the solutions between 2 pi and 4 pi, but just moved on. I'm going to get all those solutions, and once I know what those solutions are, I'm going to squish them up. It's easier to do with what I know, that normal sine curve, that nice flow. Same thing will go for cosine and tan. Do what I normally know, and then worry about squishing it in back at the end. So what do I think about this? I'm going to think 2 laps of the unit circle. In other words, 720 degrees, or 4 pi. That's where my mind is thinking, what are my solutions within that range? And once I know those solutions within that range, I'll squish it. But how do I show that? Well, if I look at my domain, our domain says must include 0, but don't include 2 pi. That's what our brackets are representing there. But if I'm going to think of this instead of just not squished up, but think of it as its expanded form, well, cause my period was a half, I'm going to double my domain. So 0 times 2, well, that still stays as 0. And 2 pi times 2, well, that's going to become 4 pi. You can see by writing that, I've stretched that curve back out over 720 degrees, 4 pi. It's that normal curve. I know how to answer that. And that's what I'm going to think of. And then at the very, very end, I'm going to come back and get rid of that period part. I'm going to squish it back up. So now that I've got this, I'm thinking between 0 and 4 pi. I'm now treating it like I would normally treat sine of x. So let's have a look at this. We know that that's negative half. So cause it's negative half, that should trigger a couple of thoughts for us. We know our solution's in the third and the fourth quadrant because that's where sine is negative. What do we know about sine of half? Go back to our reference sheet. Go back to our exact ratio triangles. What do we notice? Sine of a half. Well, sine of a half is 30 degrees. But this question is talking in radians. So let's deal with radians because we're going to have to. And 30 degrees is pi on 6. Sweet. We've got our related angle. We know what quadrants it's in. We know that the third quadrant is 180 plus theta. And remembering that 180 degrees is pi. 90 degrees was pi on 2. 270 degrees was 3 pi on 2. And 360 was 2 pi. So if I'm doing theta plus 180 degrees, that's theta plus pi. So my first answer here is 7 pi on 6. The next answer over in the fourth quadrant, which is 360 minus theta. So in this case, 2 pi minus pi on 6. So 2 pi take away pi on 6. Well, 2 pi would be 12 pi on 6, and 12 pi take away pi would leave me 11 pi on 6. Sweet. That's what's comfortable to us. Now remember how I described this as two laps? Well, my next solution that I'm going to write down is just 360 degrees away from the first solution I wrote down. Or in this case, 2 pi, an extra 2 pi away. So now I'm going to do 7 pi on 6, the first solution, and then just do that a full lap later, which is a full 2 pi later. So 7 pi on 6 plus 2 pi, well, 2 pi, remembering that's 12 on 6. 7 plus 12 is 19. So the next solution I have is 19 pi over 6. The solution after that, which was, so I've done that. The next one was 11 pi on 6. That was my first rotation. In the second rotation, it's 2 pi, a full 360 degrees later. So I'm going to add 12 pi on 6 to that, and 11 plus 12 is 23 pi over 6. And then the next solutions after that, again, would be just to add 2 pi onto what I've just done. Because remember, we've got that rotation, that cyclic, that repetition where it's this curve, the same curve, the same curve, the same curve. So those solutions would always be just, once you found the first couple, 360 degrees later, 360 degrees later, or if you're dealing in radians, 2 pi, 2 pi, 2 pi. A handy thing to do is, just in case, because we've done something with our domain, because our domain's now extended to 4 pi and we've done something with our period, might be handy just to chuck a few extra solutions in there because they're just repeated of each other, just to make sure we're not missing anything. So what I'm going to do, the next solution is going to be 2 pi after 19 pi on 6. So 19 pi on 6 plus 12 pi on 6, 19 plus 12 is 31. So I get 31 pi on 6. I might just leave it, I'll add the next one, 23 pi on 6 plus 12 pi on 6 becomes 35 pi on 6. There's our solutions, but there's something I need to really be careful with. That these were the solutions when I was dealing with 2x. Remember how I said we're going to ignore it, we're going to deal with it as if it was fully stretched out? Algebraically, how would I get from 2x down to x? Well, I'm going to divide everything by 2, or because we're dealing with fractions and fractions are our friends and it's easy to deal with, I'm just going to multiply everything by half. 7 on pi on 6 times half, or 7 pi on 6 times half, that's 7 pi on 12. 11 pi on 12. 19 pi on 12. 23 pi on 12. 31 pi on 12. 35 pi on 12. So now I've gone from, by timesing it by half, dividing it by 2, I've taken those solutions that we had fully stretched out and compressed them back towards the y-axis. The last thing I need to check on right now is, have I got all the solutions within the domain that I was originally asked? Originally, we were asked for between 0 and 2 pi. So when we're going back and checking our answers, we're making sure that if we've got any fractions, that none of our fractions are greater than 2. 7 pi on 12 is a solution because it's less than 1. 11 pi, it's less than 1 whole. That's what I mean, sorry, less than 1 whole. 19 pi on 12, it's greater than 1, but it's less than 2. Remembering here, if my denominator is 12, 2 would be 24, so my numerator needs to be less than 24. So 19 on pi on 12 is a solution. 23 pi on 12, just a solution still. And I'm going to not include them because 31, that's greater than 2. That's 2 and a little bit now. So I should only have 4 solutions: 7 pi on 12, 11 pi on 12, 19 pi on 12, and 23 pi on 12. Let's go back over to the graph. Now when I have a look at this graph here, the first thing that I'm looking at is that solution, say pi on 12, 5 pi, 13 pi. I think I've done something wrong. But have a look at what I've got highlighted there. I've typed my graph wrong. I've typed y equals half. The blue line was y equals half. It should have been negative half. So if I scroll across to where I get negative half, there you can see where that value of negative half is. 7 pi on 12, 11 pi, 19 pi, 23 pi on 12, our 4 solutions. So in summary, what did we do? We looked at the question and we recognized that when we first looked at the question, that there was a sign of 2x there. And we know that a sine of 2x has that compression effect. It gets the normal sine curve and squishes it in. And what that means, over our normal domain of 0 and 2 pi, this curve happens twice. That's really tricky to deal with. So instead of trying to figure out all the squished up part, we stretch it out. We look at, okay, if it happens twice, where are all my solutions when I look at the sine curve in a full mode twice, which is 720 degrees, 4 pi, when it's that full. deal with everything in that big, nice, comfortable space, everything with our normal unit circle. Once we got to our solutions with our stretched out, we then did the times by half, divide by 2, which gave us that compression back towards the y-axis, and it produced our solutions. Now, the next few examples, I'm going to go through at a bit of a quicker pace now, not having to explain as much detail. So, question 2 here. Solve tan of 3 theta for equals 0 for 0 between 0 and 360 degrees. Happy days. This one we know pretty well. So if we have a look at this, the first thing I'm seeing here is 3, 3. So that is my period. Changes by a third. Everything's squished in. All right, so because everything's squished in, I've got to remember that for the end. But I'm going to leave everything else. Because this is 3, I'm going to treat this between, 360 times 3 is 1080 degrees and 0. By writing like that, that means remembering, treat it as if it was normal. Do everything what would be 3 repetitions or over 3 360s. Treat that as normal. Once I've got that as normal, bring it all back together. When do I know that tan is 0? Well, tan is 0. Tan has a value of 0 at 0 degrees, 180 degrees. That's when it's 0. It's a boundary angle. So I'm looking for when is it actually on the x-axis. So that's where our 0 would be. So in saying that, our related angles are 0 degrees and 180 degrees. So we know that 3 lots of this would be at 0, 180. That's our first lap. Now remember, everything is just 360 degrees on from our first solution. So our next one would be 360. And after 360 is 540. See how they're 360 on from our first pair of solutions. That's our second lap. Let's go now our third lap. So 360 on from what we have. So 360 on from what we have is 720, and 540 plus 360 is 900. Let's just continue. I think that might be the end of it. Not sure. Let's keep that pattern going just for a little bit. So we've gone 0 and 180, 360 on from that, 360 on that. So now I need to go 360 on from 720, which is 1080. And then a little bit further than that is what's 900 plus 360, 900 is 1260. All right. And that pattern would continue. Because it was 3x, we're now going to multiply everything by a third. So we get our value of x. Well, we're going to get 0. A third of 180 is 60 degrees. A third of 360 is 120 degrees. A third of 540 is 180 degrees. A third of 720, you'll get the pattern here, 240, 300, 360, and the next one would be 420. That's that 1260, a third of that. Going back to my domain, what was my original domain? My original domain was from 0 to 360 and including it. So looking down, I'm going to kick 420 out of my solutions. It's not there. So the solution for x, when is 3 tan of 3 theta equal to 0? It's all those values there. And sliding across to the right, you can see lots of tan curves happening. because of that compression, that dilation towards the y-axis, and there are all our solutions. All right. Example 3, solve sine of x minus 250 degrees equals root 3 on 2 for 0 to 360. This one's slightly different. This one isn't so much it's not a compression towards or a dilation away from the y-axis. It's a shift. It's literally getting the whole graph up, picking it up, and moving it 250 degrees. So we need to take that consideration on. So let's think about this. This just stays the same as everything we've done. Let's deal with normal sine. After we find out all our solutions for what it would normally be, then let's move all our solutions the same way we did up earlier, where we got all our solutions and then compressed them. So what we're going to have here is x minus 250 degrees. Well, what was the change? I took away 250. So 360 take away 250 is 110. And 0 take away 250 is negative 240 degrees. So that's where I'm playing with at the moment. Having a look at this, I see root 3 on 2. Root 3 on 2, that's back to our exact ratio triangles. Root 3 on 2 is opposite over hypotenuse. So our related angle here is 60 degrees. Cool. We know that root 3 on 2 is positive, so it's in the first and is in the second quadrant. So we're still only doing one lap of the unit circle, but we've got to think here. We're going in our domain now. We've got a negative rotation. Because I've got a negative rotation and I've got a positive rotation, I'm going to do the first two quadrants that way, and when I do negative, I'll do the other way. So my solutions are, in the first quadrant, it would normally be 60 degrees. So these are my positive rotations, normally 60 degrees. Remember, the second quadrant is 180 minus theta, so it's going to be 120 degrees. Now, when I do the negative rotation, so remember what I mean by negative rotation is going that way around the unit circle, remembering how everything just flipped and became negative. So I'm thinking it's going to be negative of 180 plus theta and negative of 360 minus theta. 180 plus, so I've got negative 240 degrees, and I've got 360 negative 300 degrees. All right. Remembering our negative rotations, that's where I got those from. If you need more explanation of that, ask me later on in class. So 240 degrees, negative 300 degrees. There we go. But remember, this was before we did the shift. Now I need to apply the shift. How would I get rid of x minus 250? I'd add 250. So we're going to add 250 degrees to everything. 60 plus 250 is 310. 120 plus 250 is 370. Yep, 370 degrees. 240 plus 250, negative 240 plus 250, sorry, is 10 degrees. And negative 300 degrees plus 250 degrees is negative 50 degrees. I've done one lap each way. Let's go back and check my domain to see what I need to reject, if I need to do anything. And remember, my original domain said between 0 and 360. So I'm going to eliminate anything here that's not between 0 and 360. Gone, gone. So the solutions here are 310 degrees and just 10 degrees. And over here on the right, there's the graph of sine x. You can see the curve doesn't look quite normal. That's because it's been shifted 250 degrees. And you can see my two solutions that are inside the domain that I asked for were 10 and 310. You can see those 2 points just outside our domain. Those were the other two solutions that we just quickly rejected then. All right, guys, so just summarizing everything that we've just done there, it's when we recognize a change in our period or a shift sideways with our graph, we have to take that into consideration when we're doing our answers. And the way we deal with it is we worry about dealing with it at the very end. It's the last thing we do because it makes trigonometry more complicated going, oh, how do these things shift? The way we do it is we recognize the shift, go, okay, I'll deal with you at the end. Treat it like it's a normal curve. What would the normal sine curve be? Remember, when we say treat it like the normal sine curve, what would the normal sine curve look like? Well, if it was x minus 250, the normal sine curve goes from minus 240 to 110 degrees. So that's where we're trying to look on our unit circle. We're only going to go as far as negative 240 degrees. We're going to go only as far as anti-clockwise, the normal rotation, as 110 degrees. We're going to identify everything that we know that happens in that zone. And then for safety, just do something just outside it to make sure we haven't missed anything. Up here, we recognize there was a change in our period of 3. So instead of trying to squish tan up, what would it normally look like? What would be all my solutions between 0 and 1080 degrees? I know how to do that. It's just repetition of anything that happens between 0 and 360 degrees. Figure out what all that repetition is, then apply the compression towards the y-axis. Sine of 2x, right? That changes my 2x. That would be like the sine curve happening over 4 pi. What do I know about sine over 4 pi? What do I know about sine over 2 laps of the unit circle, over 720 degrees? Where are all my solutions like normal? And then at the end going, okay, it was 2x. Now I'm going to compress you by half. I'm going to apply that horizontal dilation towards the y-axis. That's what we do. Hope that helps. If you've got any further questions, see me in class.